Here we got another video on the shorter side where, again, I don't do too many examples, but there are more examples in the book if you want some more. So we're going to talk about equivalence classes here, obviously, and we're going to talk about them a little bit sooner than we talked about equivalence relations in the last one. So we're just going to jump right into the definition. So let's say let R be an equivalence relation. And I'm going to start abbreviating things because I don't like writing that much. Let's call an equivalence relation ER. Then the equivalence class, let's call that EC, of some element A. Oh gosh. And let's say A is some element of big A. The equivalence class of little a is written as brackets of A. This is the equivalence class. And what this is it's a set of everything that A is related to. So how would we write this? It's the set of everything A is related to. So it's the set of all elements such that A is related to that element. Oops, sorry. Well, it's an equivalence class, so it actually doesn't matter what order I write this in, right? I erased it to switch the order of this, but the order doesn't matter because we have an equivalence relation, and equivalence relations, unlike these videos, are symmetric. So I could have written it either way. So that is what an equivalence class is. We're going to do some examples and then talk a little bit about some special properties of equivalence classes. So let's start with this example where let's say S, our set that we're talking about, is the power set of the set 1, 2, 3. Remember, that is the set of all subsets of this set. And that set of all subsets includes the empty set, and it includes the domain of discourse, it includes that whole set as well. So let's say that's our set, and we define the relation. Let's say that two elements, so let's say that this is made up of little things, the power set is made up of subsets, right? Let's say that two subsets are related to each other, and remember, a lot of times we'll use that squiggle, that tilde, to show equivalence relations specifically. Two things are related to each other if and only if they have the same size. Okay, so specifically, right, the set containing 1 would be equivalent, would be equivalent to the set containing 2. They have the same size, they have the same cardinality, their cardinality is 1. Okay, so that's what we'll be dealing with here. So first thing first, I guess I spoiled it a little bit, but let's check it anyway. Is this an equivalence relation? It's a good idea to pause the video right now and see if you can kind of figure this out on your own. Of course, the answer is going to be yes, but see if you can figure out why. Make sure you can get all the checks and remember what they all mean. So again, is everything related to itself? Yes, every subset here has the same size as itself. Every element in the power set, every subset of 1, 2, 3 has the same size as itself. That size may be 0 in the case of the empty set, but yeah, they do. Let's see, symmetry. If one subset has the same size as another subset, does that other subset have the same size as the first? Yes, of course. Yeah, that's just equality. Equality is already symmetric. Equality is already a equivalence relation. If set A has the same size as set B, and set B is the same size as set 3C, do the first have the same size as each other? Yes, of course. We have transitivity of equality as well. So our answer will definitely be yes. For part B, find the equivalence classes. And I'm going to show you how we write the equivalence classes as well. I'm going to do my first abbreviation here. Find the equivalence classes. So let's think first about what equivalence class means in this case. Equivalence class of an element is all the elements that are related to that element. So it's like a family. everything that's related to that person. Okay. So what kind of families do we have here? Well, things are related to each other if they have the same size. So the families are going to be the things of size 0, the things of size 1, size 2, and size 3. And there's nothing outside of those 4 families, right? Because every subset here either has size 0, size 1, size 2, or size 3. So it might be helpful to write out the power set. It'll take a while, but it would probably be helpful to write that down, right? If you'd say, okay, this is going to be the set containing the empty set, all the sets of size 1, blah, 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 all the sets of size 2, blah, 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 and then the whole set as well, right? If you actually went and took the time to do this, it's a good habit to be in. It's a little tedious, but it would help. So the equivalence class, essentially the family of size 0, is the equivalence class of the empty set, right? This is a member of the power set, so it has an equivalence class. And that's just going to be the set of all things that are related to the empty set. What's related to the empty set? What has the same size as the empty set? Only the empty set. So again, it's fun. We have a set containing an empty set. Sets of sets. So many sets of sets in this class, actually. Okay, and now we can go on to something a little bit more interesting. What's the equivalence class for sets of size 1? And maybe you write this like this. The equivalence class for the element of the power set, which is the set containing 1. It sounds a little silly, but that's what we have here. This is going to be the set of all the things that are related to the set containing 1. And again, related here means they have the same size. So the set containing 1 is, of course, related to itself. Everything's always related to itself in an equivalence relation. That's the reflexivity requirement. And it's also related to the set containing 2. These have the same size. What else has the same size? The set containing 3. And that's the equivalence class, essentially the family of 1 elements. Family of none elements, family of 1 elements, and we'll, so on and so forth. Now you could have also written, I've spoiled this a little bit, right? You could also call this, right, instead of just Jason's family, you could have called it Jonathan's family, right? We have the same family. We're related to each other. Let's talk about direct family, I guess. And you could have also called it Chris's family. This works especially well since I have 2 brothers, right? Whichever way you call it, Jason's family, Jonathan's family, Chris's family, it's the same family, all right? And it's got these 3 elements in it. So you don't have to. And in fact, usually I will only be giving it 1 name. I'm just going to say Jason's family. But you could call it by other names. And we can continue. What's the family of size 2? Again, you could choose any set of size 2 that's in this power set. And you could go on and fill this out, and we'd have the family of size 3. And that's only one thing. You could write this out as well. So you can totally do this. You know power sets. You know what things have the same size. It's just going to be sets of sets. You can fill this in. Let me know if you have questions, though. I don't mind answering them or talking about it. And yeah, that's the video. Okay. So just the last point to summarize, right, is if you have an equivalence class, let's say you have 2 equivalence classes, and A is related to B, what does that mean? That means these 2 things are equal to each other. The same equivalence class, right? And similarly, if you have 2 things and A is not related to B, what does that say about these? Not only are they not the same equivalence class, they have no overlap. Okay? So this is going to say that their intersection is 0. And this is going to be a very important property because we're going to talk about how equivalence classes have to do with partitions. And what was one thing about partitions, right? They can't have any overlap. And they make up the whole set. Well, you'll notice once you fill this in, this equivalence class just happened to make up the whole power set. And each equivalence class is either the same equivalence class or has no overlap. So there's going to be some connection with equivalence classes and partitions. What do you think it's going to be? Well, you're going to have to stick around and find out. Or you could Google it. Or you might just already know. But let's say stick around and find out. Have a good one. Bye.